Hi, welcome to SP 7.3, Theoretical and Experimental Probability. So you've done probability before in grade 6. The difference is now, instead of just finding the probability out of maybe, say, flipping a coin, now you're going to do two independent events. So maybe you're flipping a coin and then you're also drawing marbles out of a bag, and you're going to find the probability of those two combined things. So remember this very important message: when you have two independent events or any number of independent events, you have to multiply those events. So let's skip down to the bottom of these outcomes. You know that probability is usually represented by fractions or decimals. Okay? And so taking those fractions or decimals, and now we're multiplying them because there's two separate events happening. Okay, back up to the top. Explain what probability tells about a situation. So is it good odds, bad odds? Is it likely to happen, unlikely? Is it certain, 100%? Is it impossible, so 0%? Providing an example of two independent events, such as, so here's some examples. Spinning a 4-section spinner and an 8-sided die, so two separate things. Tossing a coin and maybe rolling another die. Tossing two coins. So in this case, it's the same instrument that we're using, but because there's two of them, we are going to take the odds of one coin and multiply it by the odds of the other coin, or rolling two dice. So why are these called independent? Well, if I flip a coin, I can either get heads or tails, right? And then if I flip that same coin, I can still get heads or tails. These are called independent events because it doesn't matter what happens on the first flip. It is not going to affect the second flip. If I get heads the first time, that doesn't mean anything. I could get heads or tails the second time. There's no guarantees. When we talk about, in theory, theoretical, the theory is that you have a 50% chance of getting heads on the first one, and you also have a 50% chance of getting heads on the second one. So 0.5 times 0.5, or 1/2 times 1/2. Make sense? And so you never know what you're going to get when you actually do the experiment. It can differ from your theory. Even though you have it all worked out and you think you have, a 50% chance, you might not roll head, or you might not flip heads for 3 or 4 coins in a row. You never know. When you do the experiment, it could come out all crazy. The more you do your experiment, though, if you have several flips, they should align with your theory. If you only flip once, that isn't likely going to align with your theory. But if you flip that coin 100 times, it should get closer to theoretical probability the more times you do it. All right, we have a couple examples of sample space. That just means all the possible outcomes for each of the two independent events. Now, there's different ways to do this. We can draw a tree diagram. You can use a table or some other sort of graphic organizer. So I have a few examples coming up. Determine the theoretical probability of an outcome of two independent events. Okay, we've already talked about that one. Conduct an actual experiment and maybe chart it out. Solve a problem using two independent events. And explain how theoretical and experimental probabilities are related and why they cannot be assumed to be equal. So we just talked about that one. Although, like I said, the more you do your experiment, the more times you have an experiment going, the closer it should get to your theoretical probability. And again, it's a fraction, a percent, a fraction, or a decimal. The chart at the top shows the sample space for a pair of dice. What they don't tell you here is that it's actually the sum. They're adding the dice together. So if you rolled a 1 and a 1, the sum is 2. If you roll a 4 and a 5, the sum is 9, which is just the same as if you were to roll a 5 and a 4. So they've charted the sample space out to show that these are all the sums that you could get. This also shows that 7 is the most common sum. It happens 6 times in this chart. So 6 out of 36 times. And then you could use your calculator to divide. A fraction bar means divide. So 6 divided by 36, and that would give you your decimal, which would equal your percent. At the bottom, they've shown the sample space for coins. On the first toss, you can either get heads or tails. So let's say we got heads, and from that coin on the second toss, again, your odds don't change. You can still get heads or tails. So let's say we got heads again. And then on the third toss, again, you can have heads or tails. Let's say we got tails. And so that means that your outcome is heads, heads, tails. And so maybe you would have a question that says, out of all of the outcomes, if you were going to toss a coin 3 times, what are the odds of getting all tails? Tails, tails, tails. Well, if you're tossing a coin 3 times, here are all the possible outcomes. 5, 6, 7, 8. There's 8 different combinations that you could get, and only one of them shows all tails. So it's a 1 out of 8 chance. And again, you can use your calculator to find the decimal on that. So when you're doing 2 independent events, remember you have to multiply them. So what are the odds of spinning yellow on this spinner? Hopefully you said 1 out of 4. What are the odds of rolling a 6? Hopefully you said 1 out of 6. Now, I find multiplying fractions easier than adding or subtracting because you don't need to find a common denominator. You can just multiply straight across and multiply straight across. So 1 times 1, 4 times 6. Your odds of getting yellow and rolling a 6 are 1 out of 24. So if you did an actual experiment, remember this is just theory, that's the theory. Theoretically, you should get it within 24 tries. But you could do an experiment and roll it 100 times and never get the combination of yellow and 6 because experiment doesn't necessarily match the theory. So here I have some bags of marbles. What are the odds of pulling out a green marble from bag number 1? Well, there are 4 green, and the total number of marbles inside are 10. So it's a 4 out of 10 chance. If you want to reduce that, you can say it's a 2 out of 5. Okay. Now, what if I wanted to put all the marbles back in and draw again, and again I want green? So we're still dealing with your 4 out of 10 chance. And I'm going to put that marble back in, and again, so there's still 10 marbles in my bag, and pulling green, it's 4 out of 10. So if I've reduced my fraction, it means 2/5 times 2/5 times 2/5. So multiply straight across. 2 times 2 times 2 is 8. And 5 times 5 is 25. Times 5 is 75. And that does not reduce. So those are my odds of pulling green 3 times in a row. But what if we didn't replace the marbles? What if I said, okay, I'm going to pull the blue, I'll pull the red. So what are the odds of pulling red and then another red and then another red, and we're not replacing those marbles. So the odds of red on the first one are 3/10 because there are 3 reds out of 10 total marbles. And say if I leave that marble out, we can't count them anymore because it's in my hand. So now what are the odds of pulling red? Well, now there's only 2 left and there's only 9 total. Okay, and on the third try, there's only 1 marble left that's red, and there are 8 in total. So I would multiply those 3 fractions to get my odds of pulling all 3 red ones out of the bags. 3 times 2 is 6 times 1, 6. 9 times 8 is 72 times 10 is 720. So not very good odds. 6 over 720. Quite often in probability, the question will revolve around a deck of cards. And so we've got a sample space here drawn out of the deck of cards. So there's a few things you need to know. First of all, a deck has 52 cards. There are 13 in each suit. There are 4 of each card. Okay, so for example, if they say, what are the odds of drawing a 4? Well, here are all your 4s, and so you can say there are 4 out of 52. Or you can say it this way, saying, well, there's 1 in every suit. 1 out of every 13 cards is a 4. And mathematically, if you reduced 4 divided by 4, 52 divided by 4, that's what you'd get. So just different ways to say the same probability. There are 3 face cards in every suit, so 3 out of 13. So let's do a little experiment here. What are the odds of drawing a card greater than 8? Well, here are all the cards greater than 8, so you could count them all up and say that that's your number out of 52, or you could say just within each suit there are 5. So 5 out of 13. And if you wanted to do it twice, you're going to cut the deck 2 times and get a card that is larger than 8. Remember that in that independent event, if there's 2 events, you need to multiply. And so the odds would be the same, 5 out of 13 times 5 out of 13. Multiply straight across, 5 times 5 is 25, and 13 times 13, 169. So keep this little handy chart in mind when you're working with cards and probability. And Mr. Dinosaur says, if you're 1 in a million, does that mean that there are 6,000 people just like you? So I'll let you do the math on how they got 6,000, but I'll tell you that 1 out of a million, obviously million is not the population of the world. They must have multiplied by something to get the population of the world, and they multiplied by the same number on the top, which is 6,000, to get 6,000. So we're going to multiply by 6,000 top and bottom. What you do to the top, you must do to the bottom. And so we have a 6. We have the 3 zeros from the 1,000, and we have the 6 zeros from the million. Our new number, these are the nobodies, these are the thousands, these are the millions, and we have 6 billion, which is the estimated population of the world.